Hi, everybody. Hey, Dr. Menace here. I'm trying to introduce the whole idea of gases to you today, and then we're going to have a series of videos on gases, okay? Most people know what a gas is. A gas is, a gas. I don't know. Gas versus vapor. Carbon dioxide gas is what you breathe out. Water vapor you breathe out. Vapor is below its boiling point. Gas is above it. Not a big deal. But what is a big deal are solids versus liquids and gases. Solids are really tightly packed. So if you had a solid, it'd be all bounced in there, all tightly packed in there. Okay. Liquids would also be tightly packed. Okay. They're still touching. The gig is like you want to sort of visualize a ball pit. If some jerk goes in there, glued all the balls together, so they could do, you could shake the ball pit. That'd be about it. You got yourself a solid. Okay. Heat it up so that glue that's holding those balls together is loosened, so the balls can sort of roll around, but they're still stuck together. All right, tough to walk on. The solid you can walk on easy. The liquid you didn't be rolling under your feet. Okay. Gases, well, now you're taking those balls out of the ball pit and chucking them far away from each other. They no longer touch. They're really, really far away from each other. All right. There's no connection. So that's why, all solids can do is vibrate. All, liquids can rotate like those balls we were talking about. Well, gases, they can translate. They can move across space. They can diffuse. Gases always move from where they are to where they aren't. Okay, not a big deal. Or if they go from high pressure to low pressure, from where they are to where they aren't. That's the nature of a gas. So what makes a gas? Well, there's that, but we have to do kinetic molecular theory. A lot of our laws, we're going to move out of the real to the ideal. And for the most part, unless you really work at the extremes of conditions, it doesn't affect your calculations. So that's why we use these set of assumptions. They're really good assumptions to work with. Okay, so basically we have this idea that each air particle, like each gas particle, doesn't occupy any space. And that's probably the hardest thing for us to talk about. Okay, so let's put that on the back burner for a second. Okay, as particles move through space, they're going to go in straight lines. So if you have our little room here, the particle is going to take off, go in a straight line. Okay, and it bounces off the walls of the container there. We're going to say no energy is transferred, that it's a good bumper if you shoot and pull and it goes off. Okay, angle of incident equal angle of reflection, no energy is transferred. Okay, that energy of the gas particle is reflected in its temperature. Okay, how fast it's going is how much energy it has reflected in the temperature. But we say, hey, there are no attractive or repulsive forces between the particles. Well, it's rare that gas particles would collide with each other. I mean, blindfold yourself on a football field with your friend at the other end and run aimlessly about the field and see if you run into each other. You might. Odds are you're not. Okay, so if one gas particle is here moving across space and the other particle's there, potentially maybe they'll interact and hit each other. Well, we're saying if they do, there's no attractive or repulsive force there. Nothing goes on. In the real world, they do, okay? But for right now, don't sweat it, okay? Nothing's going to happen there. As far as why we have to say that, hey, this whole assumption that each particle doesn't occupy any space, let's just talk about a room. Let's talk about 1,000 square foot room, like my classroom, okay? If I'm the only one in it, how much space do I got to move around in? That's square feet. I would have about 999 square feet. I can't go where I am, so I don't have all the space available. And that doesn't really make that much of a difference, does it? Not really. But if my class of, 30 some odd kids are in there, and say I have to watch another class of like 30 some odd kids, it can fill up. And once like any room gets really full, you're well aware of the space occupied by other people already. Well, gases are really, really small. So for other particles to have any impact upon their space, not really. So we're going to assume the gas particles, you don't have to do 1,000 square feet minus the volume of the particle because it doesn't really matter. It's going to be 999.999 square feet. It's tiny. Okay, so it doesn't really matter. Where it does matter is in this volume for you to understand diffusion, so to speak. Say you have a 2 liter bottle. Now we have 2 liters of space. I want a bigger, fatter pen. So we have 2 liters of space. All right. If we put gases in there, do we have 2 liters of gas? Does a 2-liter bottle really hold 2 liters of gas? It would if it was a liquid or a solid. But gases, remember, there's a lot of empty space between the particles. What 2 liters really represents is the available space for the particles to move through, which is kind of neat. Because if we have that particle moving through space, okay, say we introduce another gas particle, okay, well, that gas particle's movement of space is unaffected by the presence of those other gas particles because they're so tiny, lots of space in between. It has an advantage. You don't surround yourself by CO2 by breathing out. The CO2 diffuses out, oxygen diffuses back in because there's so much space between the gas particles. Okay, that's why gases can move from where they are to where they aren't, high concentration to low. Okay, well, the properties we're going to talk about are 4. We're going to go from the most complicated to the least. We have pressure, and that's when they collide with the walls of the container. Okay, and so I think it is force per unit area, but it's easier to just talk about in terms of collisions. Okay, collisions with the walls of the container. Okay, the units are rather cumbersome. Mainly my students, when you're first learning this, my students learn that, hey, the unit that isn't familiar, that's pressure. Atmospheres, kilopascals, millimeters of mercury. Millimeters of mercury is literally the height of a column. You fill a column full of mercury, the more air that's available out here to push on that column and push it up, the more pressure that column rises. The less air to push on it, the column falls back down, the column decreases. Okay, that's why literally millimeters of mercury is the height of the column. If you pay attention to the weather, they'll say 30 inches of mercury. It's the height of the mercury column. Okay, long ago, the Torricelli did a lot of work with barometers, and later, after his death, I think, after his death, they named Torr, short for Torricelli, a unit in his honor. Okay, so Torr and millimeter mercury are the exact same thing. Okay, as far as pressure goes, what does this force per unit area gig really represent? I like to go to a shoe. Okay, let's do somebody's shoe that has a heel that's 2 by 2, it's 4 square inches. Okay, if that person, that woman, let's just pretend it's a woman because I'm going to put them in high heels later. I know it's sexist, but get over it. Guys usually don't wear high heels, but maybe they do. I don't know. You have a person, 140 pounds, heel, 35 psi would be the pressure because it's a force per unit area. So the force is the poundage, okay? The pounds, unit area, 4 square inches, per means division. So you have 35 psi. So say that person stood on your hand, you have 35 psi. It might hurt a little bit, but you'll be all right. What if they had a tiny, 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 tiny little heel? Okay, 140 pounds an hour for say a quarter of a square inch. Okay, now you're talking some solid pressure, 560 psi. That's why they call those heels stilettos, because it'd be like a little knife in the back of your hand. That's what we mean by force. Force per unit, by pressure, force per unit area. Okay, but seriously, for gases, think of it as collisions. Okay, temperature is going to relate to what we call the speed, because temperature is the average kinetic energy of the particles. Okay, just the average kinetic energy. Well, kinetic energy is 1/2 mv squared, which relates to the velocity. If you take AP or you're a college student, you're going to learn that about root mean square velocity, which would be a little bit different, but true, always true. Temperature relates to how fast you're going. Okay, and so if you increase the speed, you're increasing how fast they're moving, which is going to impact the collisions with the walls of the container. Okay, so we really need to understand that temperature is the speed, pressure is the collisions. Temperature is 2 units, Kelvin, degrees C. They relate via that little groovy little conversion. You add 273. If you want to be technical, it's 273.15, but when you add least number of decimal places, it all goes away. And I'm babbling, so just ignore that. Add 273, you'll get your Kelvin. Okay, why do we use Kelvin? Because it's an absolute scale. Okay, temperature is relative to the freezing and boiling of water. I'll show you why right here. Okay, say you double the temperature. Okay, if you double the temperature, okay, well, think about what we said about collisions. If you're doubling the speed, will that really double your collisions with the walls container? I mean, think about it. If you're going twice as fast, it should impact how often your ball bouncing back and forth in there collides with the walls of the container, but it really doesn't. Okay, the way it would relate to the collisions is via this tiny, tiny little increase in the Kelvin temperature. There's a tiny change in the kinetic energy, which is based on the Kelvin temperature, and that's what we have to use Kelvin. For gas laws, everything that we derive today in the later videos, for them to apply it, it's always in Kelvin. Always, never degree C. Okay, degree C baud. No, just kidding. Okay, anyway. Volume is kind of obvious. If we talked about it, it's the available space. The units aren't so obvious. Liters, good. Milliliters, good. But sometimes students, when they're seeing cubic centimeters or cubic decimeters instead, which is the more modern version, they freak out about it and they want to cube the values or something like that. Cubic decimeters is just a unit. Don't touch the numbers. Cubic centimeters, just a unit. Don't touch the numbers. Don't touch the values. Where it comes from is, think of a cube about, you know, not really that big, a little bit bigger, a cubic decimeter on the side. To calculate the volume, it would be the side cubed, which in this case would be 1 dm times a dm times a dm. So in this case, it's 1 dm cubed. Okay. Well, if you filled that cube with water, think, okay, you'd have a liter of water to fill that cube. And so a cube that's 1 decimeter on the side has 1 cubic decimeter as its volume, which holds a liter. So that's why they're all the same thing. Okay. We have our particles colliding with the walls of the container. They're moving at a certain speed through a space. How many you got? Well, that's the moles. Moles is our unit for counting. It is a symbol of N, a unit of moles, just like volume has a unit of V, a unit of liters. Moles, the symbol in the math equations will be N, the unit mole. The reason it's an N is it's the number of moles. So if you always think of it as the number of moles, the N makes sense. Okay, well, that's all I got for you on this introductory to gases. I hope you learned something. I'm Dr. Manis. I'll talk to you later. Take care.